Hello, I'm making this video basically to explain what this moment area method is. And the reason that am going to talk about this particular method for beam deflections is this method is probably one of the most one of the methods which is commonly taught in your undergraduate programs, but most of the books which you actually refer, they actually don't explain this particular method accurately enough. In general, you would be remembering this method, and most of you might be thinking that this method says um, the area of m by ei diagram being equal to the deflection, and you may also, I'm sorry, it being equal to the slope, not the deflection. And you may also be thinking that the moment of this particular area, moment of the m by area of the m by a diagram equal to deflection. So this is what most of you would have been thinking till now through most of your textbooks, because it just so happens that these two statements are actually not true. It just so happens that you come across examples like you know let me draw a better straight line, a cantilever, and you may be coming across you know, probably beams like this. And the particular thing about this is for both this cantilever beam and for the simply supported beam, each of us know that the location of the maximum deflection is going to be at a certain place. For example, if you take this, you know for sure that this is where the maximum deflection is, and here you know this is where the maximum deflection is. And what you particularly also know that you know for this case, the slope here is 0, and for this you know that the slope at this end is 0. And it just so happens that in these particular two cases, if you actually find the area of the m by a diagram about this end over here or about this uh, middle point over here, it just so happens that you actually end up getting what the uh, what the slope and the deflection of the particular uh, beams are. However, uh, if you have a very general case, for example, say a case like this, a very random beam with a random deflection, and you don't particularly know where your theta is 0. Okay, you do not know where your theta is 0, and you do not know correspondingly where your maximum deflection is. And in these two cases, it's not very viable to use directly. You cannot directly say that the area of the m by diagram is the slope, or the moment of that particular area being the deflection. That cannot actually be said. The true moment area theorem actually goes something like this. The true moment area theorem, so the actual moment area theorem says, the first one actually says that the area of the m by a diagram, this is actually not the slope at a given particular point. It is rather going to be the difference in slopes between the 2 points where you have taken the area. Now look at this particular image. So I have actually cut 2 points A and B on a segment of this particular beam, and this is the m by a diagram for the particular beam for the particular loading. Okay, this is the m by a diagram, and if I take the area of between these 2 points A and B, when I take the area between A and B, what I get is not, it's not going to be theta A, it's not going to be theta B either. It's rather going to be the difference of the slopes at the 2 points. It is rather the difference of the slope at the 2 points, and that is why if you take the area such that one of the ends is one of the ends has a slope of 0, then you may be actually getting out theta b itself, because because theta a becomes 0. That is why simply saying area of the moment m by a diagrams the slope works in case you have a case like this. And similarly, if I take, say, the area of the BMD in this region, I mean, this is the deflected chip. Let me say that this has a m by a diagram like this. Then in this case, if I take this area, then the moment of the m by a diagram will give me the deflection, because at this point theta is 0. I said only this, it is only in these cases that you can actually say either theta a or theta b becomes 0. But in general, it is going to be the difference of the slope at the 2 points. And the moment of this, moment of area of m by e diagram, this equals the tangential deviation. Please note these words: tangential deviation of point B on the deformed curve from tangent drawn at A. Okay, so this is the actual statement of the second moment area theorem. So what does this particular word mean? Tangential deviation. So that is the most important term that you need to know here. Tangential deviation of point B on the deformed curve from tangent drawn at A. Okay, so these are the three things that you need to look at. Now, what this particular corresponds to is, what is tangential deviation? This is the tangential deviation. Okay, this is point B, and I have marked T B slash A. I call that as tangential deviation of B from the tangent drawn at A. So this is point A, and if I draw a tangent through the point A, so this deflected shape at this point B is located at a distance of this much from that. This is from the tangent drawn from A. So this green line is the tangent drawn from A, and this is where the point B is on the deformed curve. So this is known as the tangential deviation of point B from the tangent drawn at A. Okay, so this is actually given by the moment of this area between A and B taken about point B. So you have to take it, you have to take B where the section is taken, and A usually corresponds to where the tangent is drawn. That is what B is, where you take the section, which means the place where you want to find the deflection, and A is the location where you have drawn the tangent. Okay, and so you have a question. This is the area. Okay, this is the area for which you want to take the moment. Now, do you take moment about A or you take moment about B? That is the question. You have to take it about B, or you have to take it about the location where you want the deflection. Okay, you have to take it about the point where you want the deflection. So this is what the actual moment area theorem says. Now the problem with this is many times, no, it's not. One problem with this is you necessarily, you you always necessarily you need to know the deflected shape. So what does this mean? You need to know exactly where slopes are 0, where slopes change sign, where the reflections change sign, or what basically I'm trying to say is your deflected shape should be depicted accurately. So you have to depict your deflected shape accurately. If you draw a deflected shape which is not actually right, then you may whatever you get from the moment area theorem will not work out. So what I basically mean is, if I have a cantilever, if I have a cantilever with say a UDL, forget it, say with a point load. Okay, now I should necessarily know that the deflected shape is going to look like this. Okay, I should necessarily know all. No, I should necessarily take care of all these things and make sure I have drawn all these points correctly on the deflected shape. Okay, so in this case, I should know where are my slopes 0. It's 0 over here. Does the slope change sign anywhere? It doesn't. Do deflections change sign anywhere? It doesn't. And I know that, so therefore, this is an accurate representation of the deflected shape. So for this, I cannot draw a shape like, say, I don't know, I cannot draw a shape like this. Okay. I mean, it's obvious, anybody who looks at this beam knows that this is going to be the deflected shape and not this. But in certain cases, if there is a complicated loading and you do not know what the deflected shape is going to look like, you need to make it as close to the actual deflected shape as possible, or the moment area theorem will not work as you expect it to. Okay. So for this one, let's just take a look at a simple example, how to actually use this moment area theorem. So I'll draw a beam. Okay, with um, simply supported, just to make it quite simple. And let me give it a load of say 20 and 30. All these being separated by 5 meters each. All right. So 5 meters each is the spacing. Sorry. Oh God. Better put a file which looks like a 5. 5 meters, 5 meters, A, C, D, B. Okay. So next what I need to do is I can go ahead and draw the BMD for this. You can just make a rough calculation. Normally you will get that RA will come to be 23.33 kN, RB will come 26.67 kilonewtons. And this, you know that this BMD is going to look in the form of uh, straight lines. So let me just find the salient points. So MC, moment, bending moment at C, is going to be nothing but 23.33 into 5, which is 116.65. And MD is going to be 23.33 into 5 minus, I'm sorry, into 10 minus 20 into 5 and giving me 133. Okay, so this is my BMD. Now what I can do next is I can, these are my salient point bending moments. Now I can draw my BMD. All right, these are my axes for my BMD. Uh, All right, so let me use a green color for this. Um, at 5 and at 10, 15. So these are my, and I have values 116.65, 133.3. So let me just connect up the points. So 116.65, come on, okay, somewhere over here, I guess. And 100, oops, oh, come on. Uh-oh. Why does it, um, okay, turn off snap to grid. And 116, here it will be 133.3, and coming down to 0 at x equals 15. Okay, so this is my BMB, or my, assuming that my EI is constant for all parts of the beam, this is my M by EI diagram with all positive moments. Okay, now let me say that I need YD and YC. What I also need in this case is I also need, as I told you, an accurate enough representation of the deflected shape. Okay, so I know that my deflected shape is definitely going to look something like this. Of course, you'll have a smooth curve. Let me try to make it as smooth as possible. Okay, so this is what my curve may look like. So this is Y C Y D. So what do I need to do? According to this moment area theorem, I need to get the tangential deviation of point B on the deformed curve from the tangent drawn at A. B should be chosen as the location. In this case, what do I know? I actually do not know anything, right? What do I look for? I look for, is there any place where the slope is zero? The slope is going to be zero wherever the deflection is maximum, which might be probably here, might be probably somewhere in between C and D. I am not sure of that. I don't know where the slope is going to be zero. Slope change sign, I don't think the slope is going to change sign anywhere. Deflections, they're not going to change sign anywhere. Deflected shape depicted accurately enough. Yeah, I think it's probably accurate enough because I know that, you know, you have 2 point loads acting downward. It's definitely going to undergo a sagging flexural deformation throughout. Okay, so I'm quite satisfied with the shape, but I'm not sure of anything else. Okay, I'm not sure whether the slopes are zero. I don't know much of anything else. So what I can probably do is I'll try to proceed with what this moment area theorem says. I'm going to draw the tangential deviation of point B. First, I need to draw a tangent at A. Now, what do we choose as A and what do we choose as B? Okay, so where I want the tangential deviation is required, the tangential deviation is required at the location where I want the deflection. Okay, so in this case, I want deflections at C and D. So I need to get tangential deviations underneath C and D. And what the best thing to do is uh, take one end, probably you can take end A, and draw a tangent at A. I hope this is looking something like a tangent. Okay, so I've drawn a tangent from A. So this is A, C, D, B. So I've drawn tangents at these locations, and I'm going to mark out the tangential deviations. So mark out the tangential deviations. Okay. So the tangential deviation is the deviation from the point on the curve to the tangent which was drawn. So my tangential deviation becomes, this is T C slash A, meaning the tangential deviation from C to the tangent drawn from A. And see, this is C T D slash A. Okay. Now my job is to find TCA and TDA, which is nothing but the moment of the M by EI diagram from C to A or D to A, the moment taken about the point C or the point D. So let's go ahead and do that. So this is my uh, M by EI diagram. So I have two triangles and a trapezium. So let me mark these shapes as 1, this together is 2, and this is 3. So areas of these shapes is, one is half into 116.65 into 5. This is 291.625. And then I have a trapezium, half into 5 into, no, both of them added together, 116.65 plus the 133.3, which is 624.95 .95. And the third area is half into 133.3 into 5, which is 333.325 approximately. And this totals to about 101,249.9. Okay, so these are the areas. We will of course require them for the slopes. Now what I want is moment of uh, I need moment of one of these areas. Now the question is, I mean, how by doing the moment of the area, I will get only TCA or I will get TDA. I will not get YC or YD. I will not get YC or YD. I will neither get this. I will neither get this by taking moment of the area of the M by A diagram. I will only be getting the tangential deviation. I require the deflection, not the tangential deviation. So the workaround for this is, you see the tangent over here. Let me just extend this tangent a little more and take it all the way below B. Okay, let me take it all the way to below B. Now the interesting thing about TBA is TBA is such a large value, but at this location you know that YB equals 0. Okay, YB equals 0. All right, and I also know that uh, if I take say this triangle, and if I take this whole triangle, they will both be similar triangles. So what I'm going to do now is use similar triangles with the values of YC, with the values of TCA and TDA. TBA being a known value because it's now all this full thing is TBA. Okay, let's proceed with it. So first thing, let me find moment of this area. Okay, moment of whole area about B. Why do I need this? This will give me TBA because I've taken the whole area and I've taken moment about point B. So that will give me what the TBA is. So this is given by, uh, so basically I'm going to do one shape times distance from B to the centroid of this, plus this trapezium area into distance from here to the centroid of this, plus the area number 3 into distance from here to the centroid of this. So that gives me 291.625 into 10 plus 5 by 3 plus 624.95 into 5 plus 5 by 3 plus 333.325 into 2 times 5 by 3. Okay, these are all just locations of centroids, so just verify them. So this whole thing gives me 8679. So this is equal to 8679. Next thing that I need is say TCA. So for this I get moment of area between area of M by A diagram, area of the M by A diagram between A and C gives TCA. So basically that is, so this whole area into distance from here to the centroid plus this whole area into the distance from this to this centroid. Okay, so now I'm taking moment of the areas from C because I'm doing TCA now. Okay, so this is 291.625. Oh, that is D, right? So, oh, this is point D. So um, TDA and D. So this is point D. So from point D to the centroid plus this whole area times point D to the centroid. So 291.625 into 5 plus 5 by 3 plus 624.95 into 5 by 3, and this gives 2985. Okay, so I have 2985 and 8679. Of course, this is an M by EI diagram, so all of them are divided by EI. But anyway, EI will cancel out because everything is CI. So now we have similar triangles. Let me call this point as D dash B dash. So from triangles A, DD dash and A, BB dash, I have, so this divided by this distance equals this divided by the whole distance. So this is TBA, this is TDA plus YD. So I have TDA plus YD divided by the distance is 10 from A equals TBA by 15, giving me TDA is what, 2985 plus YD divided by 10 equals 8679, and this gives me YD equals what is this, YD equals uh, 86, this gives me 2801, and let me just introduce the EI which is missing from here, 2801 by EI. And I can do a similar thing with to find out YC. So from the smaller triangle, oops, I have not found out uh, that C dash, small eraser. So similarly I can find the moment of M by A between A and C equals TCA equals um, 291.625 times 5 by 3 equals 486. All right, by A. Okay, so basically it is nothing but this area, because I've taken C now, it is going to be nothing but area number 1 times the distance from here to this centroid. Okay, that is what is this. And now again from triangles ACC dash and ABB dash, TCA plus YC by distance to C is 5 equals TBA by 15, giving me 486 plus YC by 5 equals 8679 by 15, giving me YC equals 2407 by EI. All right, 24707 by EI. So these are the two deflections under the points C and D. So if you know the value of VI, you can go ahead and substitute. You can find out what the deflection of the points are. Okay, so this is 2407 by EI, and this is equals to 2801 by EI, 2801 by EA. So these are my deflections below the 2 points. And if I want to find the slopes, it's just the areas. So area between uh, say A and C equals 624, which is nothing but theta A minus, I'm sorry, it's theta C minus theta A, because you drawn the tangent from me, so this is theta C minus theta A rather. Okay, so this is 624 uh, I'm sorry, this is nothing but, so the area between A and C is nothing but 291.625 plus 624.95. So 291.625 plus 624.95 equals theta CA, which is basically the difference between the slopes at C and A. Okay, and this is the problem. We can see that uh, the slope below C will be quite less, but it's not going to be zero. So unless we know that one of either theta C or theta A, unless we know that either theta C or theta A is zero, we cannot find out the other. So this is where it becomes useful, that if you know where theta is equal to 0 degrees, then you know theta, x bar A, for example, is equal to theta A, because one of them is 0. Okay, so this is you cannot absolutely find out what the slopes are. You can only find out the difference of the slopes. So probably what you could have done is, if you can find out that, say, uh, slope here is 0, then if you take area up to this location, then I can get what is actually theta A. I can get what is theta A if I know that at this point, say, x here if theta is 0, then I can find out what the value of theta is. Otherwise, no, it's just left in terms of two relative values. Okay, so it's just, so this is the principle. And in case you have some other type of beam, for example, if you have a cantilever, if you have a cantilever, okay, I mean, and you draw the accurate deflected shape, which is, oops, uh, okay, just a minute, sorry. Okay, forget it. Just know somehow you draw the accurate deflected shape, okay, and you know theta is 0 here. The the best thing to do is you can draw the tangent from here. You can draw the tangent from here, and once you do this, once you do this, at every point of this uh, deformed curve, at every point of the deformed curve, y say b, this is actually going to be equal to TBA because at this location it is, this tangent is in line with the reference line of the beam. This line is, this tangent is horizontal or in line with beam. So therefore at any point the tangential deviation will be equal to the deflection. So tangential deviation will actually be equal to the deflection element. So wherever you want, you can just find out what the tangential deviation is. It will be equal to the deflection. Okay, so TCA equals YC. So it becomes quite convenient because my tangent drawn at A actually becomes horizontal in line with the beam. So you just need to find out the areas with the BMD and you can directly get, and also the convenience is since theta A is equal to 0, so therefore if you get theta CA or theta dA through the, by by doing the areas of m by A, you will get directly theta C or theta A since or theta D since theta A is 0. Okay, so you have this convenience if it's a cantilever beam. In a simply supported beam, you'll need to have find out where the maximum deflection is. Say that the slope there is 0, and then you'll have to find out what the slope is. Otherwise, no, in this case, you can just find out what these things are. So anyway, the point of this whole video is to just clarify to all of you that whatever you have actually been taught in moment area methods, not always. In a lot of cases, I see that no, a majority of all the textbooks that you use, they go by this wrong explanation of the moment area method. Okay, and they also end up giving you problems which actually satisfy this definition of moment area theorem. But anyway, they have adjusted the problems to suit their definition, and that is not the right way to go about it. Okay, so that's the reason that I just thought I'll clarify what the actual moment area theorem is, and hopefully this will actually no, there are no loose ends in what you learned in your mechanics of solids. Okay, so anyway, hope you learned something new. I'll see you later with some other topic. Thank you.